to talk to all of you about dark matter puzzles in indirect searches for dark matter. So I understand that here we have physicists from a lot of different areas. So I want to begin by just saying a bit about like the puzzle of dark matter, why I and many other people spend a lot of our time thinking about it, what we think we know and what we don't know. And I'm going to try to persuade you that looking at astrophysical and cosmological data is a promising way to learn stuff about dark matter properties that we don't already know. That said, this talk is not really going to be about solved puzzles. This talk is going to be about open puzzles, the big one of which is what is the nature of dark matter and how can we learn about it? But in particular, indirect searches for dark matter using astrophysical and cosmological data have over the years revealed a number of somewhat strange like anomalies and puzzles, some of which we think we now know the origin of, and some of which are still open. So I want to take you through like a little tour of some of those because I think they're illustrative in showing how we can pull together results from different data sets to try to understand what's really going on in these systems. And that can tell us about novel astrophysics, as in the case of the Fermi bubbles, as David just mentioned, or it might, in some cases, hold a clue to novel particle physics. And then I'll plan to spend the later part of my talk focusing on one of these excesses in particular, which is known as the Galactic Center Excess. And this is a puzzle that has occupied the field for a bit over a decade. At this point, there's been a fair bit of back and forth, so I'll try to tell you where things stand. But let's begin with just what we think we know about dark matter. So we have pretty good evidence that there is a component of matter in the universe that doesn't scatter, emit, or absorb light. And I mean, it's really, we call it dark matter, it could be really called transparent matter, that this is the dark part of the definition. But it does have mass and hence gravity. When we say dark matter, this is really all what we mean. Matter means has mass and gravity. Dark means doesn't appear to interact with light at the level that we can currently detect. That's kind of the definition. We have pretty good evidence that this is about 84% of all the matter in the universe, and that's measured from the cosmic microwave background radiation, also sometimes called the afterglow of the Big Bang. So that gives us sort of a census of, in the whole universe, what fraction of the matter appears to interact through gravity, but not emit radiation. We believe that dark matter forms the primordial scaffolding for the visible universe. So this is a plot from my colleagues in the Illustris collaboration, some of whom are at MIT, showing simulations for how the structure of the universe evolves as a function of time, going from early times at the bottom of the page up to late times at the top of the page. And on the left panel, we have what we think the dark matter is doing, and on the right panel, what we think the visible matter, so the gas that's subsequently forms into stars and galaxies and the planet Earth is all on the right-hand side. And what you see is that we believe that the bulk of the matter in the universe is this dark matter, which forms this filamentary web-like structure. There are nodes of high density at regions in this web-like structure, and the gravity of the dark matter pulls the gas onto those nodes, and galaxies are formed there. So everything that we see, all the visible universe that we can see, we believe is just a small component painted over the top of this much more massive scaffolding of dark matter. We believe related to that, the dark matter forms large clouds or halos around galaxies. And I mean, this is in some ways a reversal of the order of causality from our picture of the primordial scaffolding for the universe, which seems to agree pretty well with observations. We believe that almost every galaxy is surrounded by a dark matter halo because dark matter halos are the sites where galaxies form in the first place. It's the gravity of the dark matter that causes the galaxy to form there to begin with. So all of those are positive statements about how dark matter behaves, about how it's distributed through the universe, about how much of it there is, about how it attracts visible matter. But there is also a pretty important negative statement about dark matter, which is if it has interactions with other particles that are not gravitational, we have not yet detected them. So we can place an upper limit on the strength of those interactions just from the null results of existing searches. That is more or less the set of what we know about dark matter today. So this leaves open a lot of questions. So first, what we know already is enough to tell us that dark matter cannot be explained by any of the particles we know about. So basically, because from the fact that it forms this large filamentary structure, we know that it has to be relatively cold and slow moving, which lets out neutrinos. And those were our best option within the standard model of particle physics for particles that are neutral, that don't interact with light, that have weak interactions, and which are stable, so which would endure for the whole lifetime of the universe long enough to make this filamentary structure. So if dark matter is a particle, It can't be one of the ones we know about. But okay, that still leaves open a whole lot of questions, with the big one being, what is this stuff? What's it made from? Are we talking about one kind of new particle, like a heavier neutrino or something similar? Are we talking about many different kinds of new particles, a whole new dark sector of which the dark matter we see could be only one component, or the dark matter we see could be made up of multiple different kinds of particles, just like the visible matter is? Maybe we're not talking about a particle at all. Maybe we're talking about some massively composite macroscopic objects. Maybe we're talking about tiny black holes left over from the very early history of the universe, the inflationary epoch. These are, all viable possibilities based on what we know about dark matter today. You can ask the question of, where did it come from? How did we get this 84% of the matter in the universe's dark matter number in the first place? Is there some relationship between how the dark matter and how the ordinary matter is created in the universe? I mean, their abundances are only different by a factor of 5, so maybe there's a connection. Does it actually interact with ordinary particles except through gravity? I mean, gravity is a pretty weak interaction. If it has non-gravitational interactions, those could potentially leave pretty striking signals in the history of the universe. And we'll talk about that a bit more later. But if so, how do those interactions work? Is there a new particle that mediates them aside from the dark matter? And I could keep going with questions like this for quite a long time. So if you give, we're all theoretical physicists here, so if you give theoretical particle physicists a set of questions like this, then what happens is something like this. So this is a slide created by my colleague Tim Tate as part of the last snow mass process in the US, which is a field-wide planning process when we're just gearing up for the current snow mass process at the moment. If you're interested in getting involved, we do welcome involvement from people outside the United States. So this plot was meant to be sort of a general sketch of categories of theories of dark matter. I do not want you to try to read or understand everything on this slide. I think there are really sort of 3 takeaway points that I want. One is, we are not short of ideas for what dark matter could be. So everything within the red region here is a class of viable scenarios for new particle physics that, among other things, could possibly explain the dark matter puzzle. Everything outside the red region is larger structures of theoretical particle physics or physics beyond the standard model into which these ideas could fit. So that's the first thing. The problem of dark matter is not, we have no way to explain this stuff. It's, we have many possible ways to explain this stuff, and we don't know which, if any of them, are correct. The second thing is that if we could understand what dark matter is, it could possibly be a key to a much broader range of physics beyond the standard model. So like just on this plot, dark matter could be connected to new symmetries of the universe, like supersymmetry. It could be connected to new extra dimensions that we cannot directly observe. It could be related to the physics of the Higgs sector or the physics of the strong interactions through the strong CP problem and the Axions solution to that problem. It could be related to the neutrino sector. It could be some kind of like new heavy sterile neutrino. Dark matter could, as I mentioned earlier, be part of some whole new dark sector, some ensemble of new particles of which the dark matter is just the most stable. And dark matter could be our only key into that dark sector. It could provide insights into forces that dark matter experiences, but visible matter does not, in the same way that visible matter experiences electromagnetism that dark matter does not appear to. So if we could figure this out, it would already be pretty interesting to just solve the problem of what is 85% of the matter in the universe, but it could potentially also be a key to so much more. But then the third point on this plot is, at the moment, all these models are viable, which means that given the data that we have at the moment, these models generally do not make distinguishable predictions. All of these models are consistent with what I told you earlier, that dark matter gravitates, that it interacts pretty weakly through forces other than gravity, that it's cold and slow moving and massive enough to form this filamentary web structure, this cosmic web that I talked about earlier. So if we ever want to be able to, and so that's one thing. The second thing is that probably of all the ideas on this slide, probably at most one of them is the correct answer to what is the majority of the dark matter in the universe. There could be many ideas contributing, but at a guess, by a constraint, I would say that probably most of the dark matter in the universe is either one of these ideas or something that's not on this slide at all. So we would like to be able to distinguish between the possibilities here, it would be really helpful if we could see some non-gravitational interaction of dark matter with itself or with other particles. Such an interaction is not guaranteed to exist. This is an unresolved puzzle, but we look for it because it seems like it will likely be an essential clue to figuring out what's going on. So from what I've told you so far, I can already say that we've learned a good deal about dark matter from astrophysical and cosmological observations, from observations of galaxies and the cosmic microwave background and colliding galaxy clusters. So we've gathered useful information from quite a lot of data sets. And those data sets include like the cosmic microwave background from the early universe, they include radio observations, they include X-ray observations, and they have allowed us to exclude already many possible ideas for dark matter, starting with the neutrino that were not on this slide. So given that these data from the universe are extremely rich and getting better all the time, how can we use them to test for different ideas for the nature and origin of dark matter? Is there a possibility that we've already seen signals of dark matter? If that happens, what would such a signal look like? And how can we distinguish them from often complex backgrounds? So in the rest of this talk, I want to take you through sort of one series of answers to that problem, which is the indirect detection search program, which focuses on astrophysical and cosmological data and seeing effects that dark matter interactions could have on visible messengers from the cosmos. So yeah, so and then I'll give you some possible answers to this last question about have we already seen signals and case studies of how we might distinguish those signals from the background. Okay, so if I ask generally, how might I search for dark matter interactions? There is a huge multifaceted search program to look for signatures of dark matter, and it goes well beyond anything that I'm going to tell you about today. So just want that to be clear in the first place. This is a big question. There are tons of experimentalists working on it, as well as many theorists. There's a lot going on. One standard classification which is not all-encompassing, but it's a good sort of first way to think about the problem, going back many years, is to separate the problem into indirect detection, direct detection, and accelerator searches. So the general picture here is that we can imagine a diagram where dark matter particles talk to standard model particles. And if we have dark matter particles coming in at early times and then converting into standard model particles, then we call that indirect detection. And we're not looking for the dark matter itself, we're looking for the standard model particles that are produced in the interaction. If we have our standard model particles are sitting in a box on the Earth and we bounce dark matter particles off it and then we look for how the standard model particles recoil, we call that direct detection. So here, we're controlling the target, which is the standard model particles, but we're not controlling the beam, which is the dark matter particles incident on the standard model particles. And we look for the standard model particles to recoil. And the third possibility is that we control the inputs. So we control the standard model particles coming in, but then when they collide with each other, they could produce dark matter particles. And so we can look for missing transverse energy in our detectors in company with other particles that are produced in this collision. So the colloquial, so the mnemonic that I was taught for these three strategies is break it, shake it, or make it. You can break the dark matter apart to make visible particles. You can shake up the standard model particles as dark matter strike them, or you can make the dark matter at accelerators. This is not an exhaustive list, but it's a useful way to think about ways that you might go after dark matter. For example, in recent years, there's been a lot of attention paid to situations where maybe the dark matter is capable of being absorbed, if it's sufficiently light, onto standard model particles in the course of scattering. Or you can get oscillation signals where there's a possibility, as neutrinos can oscillate from one flavor to another, you can have situations where dark matter could convert into a visible standard model particle in the presence of an external field. So many of these parts, so all the interaction structures here, production of dark matter, scattering of dark matter off visible matter, and production of visible matter from dark matter can all be tested with astrophysical and cosmological observables, as can these additional ones. So let's dig in a little bit more and talk about what kinds of interaction structures that we might look for. So these are generic interaction structures between dark matter and the standard model. And our goal is to figure out what signals of non-gravitational interactions of dark matter we might look for and how might we go after them. So the classic for indirect detection, the classic for looking for standard model particles generated by dark matter physics is a process of annihilation. So in many dark matter models, it's possible for two dark matter particles colliding with each other to make standard model particles in this collision. So this is like a matter-antimatter collision, except that in some cases, dark matter can be its own antiparticle. So this could be either dark matter, or dark matter and anti-dark matter, if they're separate. This could produce any standard model particles that we know about. So they could be quarks, they could be leptons, or they could be gauge bosons. Most standard model particles are not stable. So if you make an unstable particle in this process and it's happening out there in the galaxy somewhere, what will happen pretty promptly is that standard model particle will decay to known standard model particles. It's the long-lived particles that come out the end of this cascade that we will generally be looking for in indirect detection. Because again, indirect detection, astrophysical and cosmological searches, the physics is mostly all happening out there in space somewhere. What you're looking for is the after effects. So those long-lived known particles could be photons, they could be neutrinos, they could be electrons, positrons, protons, or antiprotons. And so there are searches for all those particles, and we'll talk about examples of each later on. There's something else interesting about this annihilation process, which is that there's a category of dark matter models. It is not the only possible category. This is, as you saw that from that giant cloud earlier, there are many ideas for dark matter. But in one classic category of dark matter models, this annihilation process is what sets the amount of dark matter in the universe. So the idea is that early on in the universe, there was a lot more dark matter, and then this annihilation process depleted it. So in that case, there's a very tight connection between the rate of this process and how much dark matter there is in the universe. And so since we've measured the amount of dark matter in the universe, you can turn that around and use that to infer what the annihilation rate has to be. And this gives you a cross-section for the annihilation, which is in natural units, 1 over the Planck mass times the temperature of matter radiation equality. And if you put that into actual units, that corresponds to about 1 over 100 TeV squared. Or if you put this in less particle physics and more, everyday and astrophysics units, you get a cross-section of about a sigma v of about 2 times 10 to the minus 26 centimeters cubed per second. So again, this is not guaranteed. The dark matter could be generated in a way that is separate from this and that doesn't give rise to this cross-section. But if we were ever to see a signal with a cross-section like this, then that would be nice, because it means that if it gets you 2 for 1, basically. If you see an annihilation cross-section like this, it's very easy to explain why the amount of dark matter in the universe is what it is. Okay, so this is one category of signals. We're looking for dark matter particles colliding with each other, making particles which subsequently decay to photons, electrons, positrons, protons, antiprotons, neutrinos, etc. And if it has this cross-section, then that's a strong signal as to the production mechanism of dark matter, as well as its interactions. We could also have a situation where the dark matter is not perfectly stable, where it can decay away with some long lifetime. The signatures of this are very similar to annihilation, except that the signal is only going to scale like 1 power of the dark matter density instead of 2, since it involves 1 particle decaying rather than 2 particles colliding with each other. So in this picture, the dark matter would, through some new physics that we would like to probe, decay into standard model particles. They would decay down to stable standard model particles, and we can look for those long-lived known particles. This kind of constraints on dark matter, this kind of constraint would also apply. Suppose the dark matter is tiny primordial black holes left over from the early universe. Those decay through Hawking radiation. So they give rise to an effective dark matter decay signal, even though the whole black hole is not decaying away. You could also have situations where there are like 2 dark matter states, and decay from the excited state to the ground state produces a similar signal to this. So either annihilation or decay, the effect is basically to let you take energy that's stored in the dark matter and turn it into visible particles. And this conversion is most prominent in regions of high dark matter density. So it's effectively regions of high dark matter density act as a source for particles. So we can search for either those annihilation decay products or their subsequent effects on the region where they are injected. What about scattering? Well, previously I had this labeled as direct detection in the plot, where dark matter comes in, bounces off a standard model particle. And if we do that in the lab, that's called direct detection. But if this process happens, it can also happen out in space. You could have dark matter particles bouncing off neutron stars, transferring energy to them, dark matter particles scattering and getting captured in the sun or in other systems. In the very early universe, scattering between dark matter and the visible matter can change that cosmic microwave background radiation from the very early universe that I mentioned earlier. If the dark matter, we generically expect the dark matter to be colder than the visible matter. So in that case, it can act as like a giant refrigerator for the universe, a heat sink that can take energy out of the visible matter and store it in the dark matter. So there are also a number of tests of dark matter scattering that can be looked for in astrophysical objects. And finally, the last interaction structure that I talked about was the possibility that maybe dark matter can just oscillate into a standard model particle. This usually requires the presence of some external field in order to allow for energy and momentum conservation. The most common example of this is the dark matter Axions. This is a new ultralight scalar particle that was originally proposed to solve problems with the strongly interacting particles in the standard model. And it has an interaction which looks like a dark matter particle and 2 photons. But one of those photons can come from an external magnetic field. So what this means is that in a strong magnetic field, a dark matter particle can convert into a photon, and vice versa. So this is dark matter that is in some ways like not very dark matter that can in fact turn into light. So the particles sourced by this kind of oscillation process can be looked for directly. If you think there's a region where dark matter is converting into photons, then you can look for that. But you can also go the other way. Photons can turn into axions, into dark matter. And since dark matter is very weakly interacting, that means that photons can sometimes get through regions that they would not otherwise be able to get to by converting into a dark matter particle to go through the opaque region and then converting back to a photon on the other side. So that can generate features in spectra of photons, like holes in the spectrum where some of them have converted into dark matter, spikes in the spectrum where there has been conversion from the dark matter. And this can allow escape of energy from regions that are expected to be opaque, such as, for example, the interior of a star. Okay, so I hope I've convinced you at this point there are lots of different ways that dark matter could interact with the standard model, and we have potential ways to go after them and look for signatures of them in astrophysical and cosmological data. So that has spurred the development of a large experimental program to look for signatures just like this. There are searches for charged particles in here. For the charged particles that I mentioned could be produced by annihilation or decay, and for neutrinos and for photons. So we're looking really at all the possible messengers, looking at a huge range of target regions and over a very wide range of energies. So the advantages of this program, I would argue, this can probe a wide variety of possible new physics at a very wide range of energies, basically whatever our telescopes can cover. The large length scales and large time scales of astrophysical and cosmological processes often allow for tests that would be basically impossible on Earth. For example, looking for decays of dark matter. These indirect searches can constrain lifetimes that are 10 orders of magnitude longer than the age of the universe. That is a test that would just be very hard to do in any experiment where you don't have all the dark matter in the galaxy to use as your test bed. Because we can look with existing telescopes at so many regions and so many different energies and so many different messengers, there are often natural cross-checks on any signal built in. If dark matter is annihilating in one region where it's dense, it'd probably better be annihilating in other regions where it is dense as well. So very often we just have automatic cross-checks built in, and I'll show you how that challenges some signals that were originally raised as possible indications of dark matter physics. And there's a natural synergy with astrophysics searches that you're looking in the same regions and you're looking for, their signal is our background and maybe vice versa. But in-depth dark matter searches often find novel and interesting astrophysics. And one example is the foamy bubbles, but I'll give you potentially another example later in this talk. And this also means that we kind of get to piggyback on the astrophysical program. Astrophysicists like to look at the Galactic Center because it's a very interesting region, but particle physicists also want to look there because there's a potential dark matter signal from that region. However, the complicating factors for any indirect search is that it's not a controlled environment. You're looking at data coming from interactions that, in your best case hypothesis, where dark matter is really annihilating or scattering or decaying or oscillating out there somewhere in the universe, you do not control the circumstances under which it happened. And this means that you're often dealing with situations where the backgrounds are pretty hard to characterize, and where also the signal may be quite non-trivial to calculate. It may rely on a detailed understanding of how the target works or of how the signal that was initially produced at that object propagates to us here on Earth. So those are the challenges. Tons of data, potential to probe signatures that just can't be seen any other way, lots of built-in inherent cross-checks, but the backgrounds are really hard. So I'm going to say now a bit more about what are the different target regions that we can look at, and then I will launch into what are some examples of cases where we've seen things that might be dark matter, but are more likely something else. So where can we look? So we can look at, so I mentioned there are, we look at lots of different target regions. So what are some possible target regions? So for most of these processes, you would like to look at regions where there's more dark matter. And that's one thing that we can use to discriminate between the possible signal and the backgrounds. So dwarf galaxies are satellite galaxies of the Milky Way that have a very high ratio of dark matter density to ordinary matter. They don't have a lot of stars associated with them. So this is very nice because they're relatively close to us in cosmic terms. They're orbiting the Milky Way. And they're pretty low background because they don't have much visible matter. So, which is to say that if you're looking for a signal from visible matter, photons or neutrinos being produced by dark matter annihilations, it's nice if you can look in a region where there aren't a lot of stars also producing photons. So dwarf galaxies are very good for this. You can look towards the galactic center. This is the opposite situation to dwarf galaxies. So the galactic center, and I'll say a bit more about this later, is potentially a region where the signal could be very large because the dark matter interacts under gravity. We believe that it builds up towards the galactic center and the dark matter density is high there. So the signal could be very big, but the background is also very big. The galactic center is the center of our Milky Way galaxy is an interesting region for lots of astrophysics. And the other thing is that while I said the dark matter density tends to build up towards the center of the galaxy, the details of exactly how that happens and how high the density gets are not well known. It depends on the dark matter model, but it also depends on the details of how the visible matter has evolved in the center of the galaxy over its history. And that's somewhat hard to predict. We can look at that. So we're living inside a dark matter halo. The Milky Way has a big dark matter halo. We're in the Milky Way. In every direction that we look, there is dark matter, which could be annihilating or decaying or scattering or oscillating into visible particles. So we have a huge area to look at here. It's the whole sky, and it's as nearby as you can get since we're in it. But again, the backgrounds like the galactic center can be quite complicated here because our galaxy is a disk of stars and gas, and it has lots of ways to make high energy photons and charged particles and neutrinos. We can look into other galaxies and clusters. So these are more distant, but they can contain a huge amount of dark matter. They can be a useful test because different clusters are at different redshifts. And if there's a dark matter signal, you would expect it to be produced at the same energy at all redshifts, which means that when we see it in our telescopes today, it will show up at different energies. So that can be a background rejection tool. The thing with clusters is that the expected signal is pretty sensitive to how smooth versus clumpy is the dark matter in the clusters, at least for signals of, for example, dark matter annihilation, which depend on the collision properties. We can look for dark matter subhalos, which would be just like little clumps of dark matter with hardly any baryonic matter. This would be a great target. The problem is finding them, because if they don't have any visible matter associated with them, it's pretty hard to tell where they're going to be. But we can do like blind searches for sources of radiation that don't have any obvious source in our galaxy. We can look at the extragalactic background radiation. If dark matter annihilation or decay has been happening through the whole history of our universe, then for the whole history of our universe, there has been a trickle of energy into visible particles from apparently nowhere. And that can modify both the cosmic microwave background radiation, but also background radiation at other frequencies. And finally, and this has been getting a lot more attention in the last few years, you can look for signals where the dark matter interacting with matter, with ordinary matter, where it is packed tightly, can have meaningful effect on the evolution of the complex object. So, for example, when supernovae go off, if you have something like an axion such that photons can convert into an axion, get out of the supernova, and energy can escape that way, then it changes the energy, it changes the evolution of the supernova in a pretty dramatic way. And we've observed some supernovae. We could look for effects of that. We could set constraints on it. And this is pretty cool because supernovae are pretty high energy systems. This allows you to probe high energy scales and high densities and high strengths of the electric and magnetic fields, which is very important for some possible signatures of dark matter interacting with visible matter. But the difficulty here is, of course, that getting any information out of these systems requires being able to do detailed modeling of the underlying astrophysical compact object. So really understanding how supernovae work, or how neutron stars work, or how whatever object that you're looking at behaves. But this is a place where there's been a lot of really interesting research recently, including by Australian researchers. Okay, so that's sort of what I wanted to say about the general project of indirect detection, what kind of signatures we're trying to look for, and why looking in these astrophysical data sets is useful. So in the second half of the talk, what I want to talk about is to give you some examples. And again, this is not meant to be, I'm telling you the solution to dark matter. This is meant to sort of give you like a little survey of, over the last few years, what are places where we've seen things that might be dark matter signals that you might want to keep an eye on, but also, what are the challenges to their interpretation as a dark matter signal. So let me begin with one that got started back when I was a grad student at Harvard, and which caused a lot of excitement in the first few years, and was actually the thing that first got me into thinking about dark matter and particle astrophysics, but which now I'm pretty confident is not dark matter. So this is the AMS-02 positron excess. So AMS-02 is up on the space station. It's an instrument measuring cosmic rays in the neighborhood of the Earth. So AMSO2 has a magnet on it, so it can tell the difference between cosmic rays of different charge. And what they found when they measured, so what they're measuring is cosmic rays of different species and different charges as a function of energy. Okay? They can't really measure very well where what direction these particles originally came from because they're charged particles, so they spiral around in the magnetic field of the sun, and this scrambles their original arrival direction. So basically, their data is number of positrons, electrons, or other species of interest. We'll talk about antiprotons later as a function of energy. So this is what the results from 2016 look like, where blue is the electron spectrum and red is the positron spectrum. And you will notice that these are quite different, and at low energies, as you might, that this is a rescaled positron spectrum. There are fewer positrons than electrons, even at these pretty high energies. They're looking at cosmic rays from about 1 GeV up to like several hundred GeV, where the calibration in EV, or 1 EV is about the energy of the light coming from your light bulb. 1 GeV is about the energy stored in the mass of a proton or a neutron. So what they found is that at high energies, there's a significant enhancement of the flux of cosmic ray positrons. And this is highly statistically significant, as you can see from this plot. Like, it is not ambiguous or experimentally in question that the red line goes up a lot faster than the blue line at high energies. So what could this indicate? Well, it was proposed at the time that one possible source for this could be dark matter. And the reason for this is just that in our universe as a whole, there's much more matter than antimatter. We know this is true. We think that the way we get most of the positrons in our galaxy under conventional explanations is that you accelerate protons to very high energies, and then when those protons hit the hydrogen in our galaxy, they can produce a spray of particles which can include positrons. That tends to predict a positron spectrum which is both much less abundant than the electrons in our galaxy, and it falls off faster as you go to high energies. This is the opposite. Here you see the amount of positrons goes up as you go to high energies. This can be pretty naturally explained if you've got some source that makes some source of high energy particles that makes positrons and electrons in equal number. Dark matter is one possible source because dark matter is electrically neutral. We're pretty sure, or at least very close to electrically neutral. It is likely to, in almost all models of dark matter, you would expect it to produce positrons and electrons in equal number. So you can ask, okay, well, how heavy would my dark matter need to be for dark matter collisions or decays to make these particles? You can see that the spectrum of positrons goes up to, a few hundred GeV. So that means that you need the dark matter to be at sort of the TeV scale, so 10 to the 12 eV or higher. You can also say, okay, so what rate do I need to get this right? You need a rate at a TeV, I think you need a rate that is about 1,000 times the thermal relic benchmark cross-section that I told you about earlier. So it's possible to get around that. There are various ways to enhance the annihilation cross-section at late times, but it's not the most natural number. Seeing this annihilation cross-section does not immediately tell you, okay, clearly we can explain the abundance of dark matter as well. So then you might say, all right, if dark matter decays or annihilates and makes electrons and positrons, maybe it will make other particles as well. Let's look for the photons that it could produce, or the protons and antiprotons that it could produce. Well, we've looked for this in other channels, and so far we have not seen a counterpart signal to this. Okay, but maybe we have dark matter that just likes to annihilate just into positrons and electrons, or muons and antimuons. That would be fine too, and not very much into anything else. That can kind of explain this signal. However, those electrons and positrons would modify the history of the universe at early times. They would ionize the hydrogen very early in its history, and if it was annihilating dark matter. And also at late times, we would expect those electrons and positrons to convert some of their energy into photons. Since they're charged particles, they like to interact with photons. And you can search for those photon signals in galaxies and galaxy clusters. And, sorry, one moment. And we haven't seen signals like that, and we have looked. Furthermore, so this is a case where those inherent cross-checks that I mentioned for indirect detection are coming into play and are telling us that it's actually pretty hard to explain this with dark matter annihilation or decay. Furthermore, I told you that probably any source that made high energy positrons and electrons in equal number would work. And from the early days of this excess, people had said, well, maybe it could be pulsars. Pulsars produce high energy, have very strong magnetic fields, and they can produce electrons and positrons just by pair production from high energy photons. So that will make equal numbers of positrons and electrons. Now, for many years, I wasn't a huge fan of this explanation just because it seemed like no one actually had a prediction for what the spectrum from high energy electrons and positrons would be, or rather there were many predictions and they vary very widely. But in 2017, people observing nearby pulsars with the Hawk telescope, which looks for high energy gamma rays, saw that there were these halos of high energy gamma ray emission around the pulsars, which could be most easily explained by high energy electrons and positrons streaming off these pulsars in large number and scattering the ambient photons up to very high energies. And so this has kicked off this whole new investigative direction in gamma ray astronomy, looking for these TeV-scale halos around pulsars, which have the ability to shed really interesting light on how particles diffuse around pulsars and the properties of the interstellar medium around pulsars. And if you ask, all right, if you take those positrons and electrons and you propagate them to Earth, could they explain this excess? The answer is yes. So at the moment, that is my working hypothesis for what is going on with this excess. So that's sort of our first case study of, oh, we see a signal. Maybe it could be explained by dark matter. How would we cross-check it? And the cross-checks seem to mostly point in the direction of something that is not dark matter physics. Okay, so that was with charged particles, where we didn't have any spatial, but I mean, this is still an interesting excess. It still could maybe be dark matter, but my feeling is the odds are strongly against it. So now let's do another example. So that was with charged particles, so we couldn't tell where they came from. If we look at photons, we typically have much more information because photons travel in straight lines or close to straight lines, depending on the influence of gravity. So there's another excess that's gotten a lot of attention in X-ray photons. So this was observed back in 2014 by two groups looking at galaxy clusters. And what they saw was that at modest significance, like 3 to 4 sigma, there appeared to be a bump in photons at energies of around 3.5 kiloelectron volts, coming from a range of different regions. And it's been subsequently, and there have been subsequent claims to observe this signal in other regions, including the halo of our Milky Way galaxy. This plot on the right is from a review by Kev-Abazagian in 2017, showing what kind of dark matter mass you would need to make the signal in the simplest explanation where the dark matter decays away and makes a neutrino and a photon, and you see the photon. And so this is sine squared 2 theta. This is a measure of how strong the interaction rate, or in other words, the decay lifetime of the sterile neutrino. And this is the mass of the sterile neutrino that you would need, or the dark matter candidate, decaying dark matter candidate. It doesn't have to be a sterile neutrino, but that's a natural explanation. And you can see, and so these different contours show like estimated predictions from different apparent detections of the excess. And you can see that they all more or less line up. They all seem to be pointing at something more or less in the same range of decay lifetime and mass. So the simplest dark matter explanation is that what we're looking at is a 7 keV sterile neutrino that decays into a neutrino and a photon. You can do more complicated dark matter models where annihilation is involved, oscillations are involved, but the simplest possibility is just that it's a dark matter decay. So then you can ask in this case, okay, like the analog of the pulsars for Pamela, what about non-dark matter contributions? So there are atomic lines in this mass range around a few keV, and I think if there are theorists working on atomic physics in the audience, you probably know more about this than I do. But none of those lines seem to naively to line up exactly right with the 3.5 keV line, but there are other lines in this area. There's also charge exchange reactions between heavy nuclei and neutral gas that can give rise to a forest of lines around this 3.5 keV area, which, given the energy resolution of the telescopes that we have so far, could potentially be mistaking it for a line signal. So the hope here is that in the next few years, as we get X-ray telescopes with better energy resolution, we may be able to figure out, is this 3.5 keV line actually a line, or is it a structure? There's also been some recent work on, so as I said, once you've got a dark matter model, you can test in other regions. There's been quite a bit of work looking at other regions like dwarf galaxies and the halo of our galaxy to try to understand if the simple dark matter decay explanation is ruled out by null results where you would expect to see a corresponding signal. So the latest of these is this paper by Desert et al. In 2018, which was just published in Science last year, claimed that by looking at the halo of the Milky Way, you can show that if there was a decay signal, you should have seen it at high significance. And the fact that you haven't seen it rules out the possibility that this is simple decaying dark matter by about an order of magnitude. However, this is an active scientific controversy. There's been arguments going back and forth in both directions, which are somewhat technical, but basically boil down to how do you model background in this region. So this is maybe something to keep an eye on, especially if you have an X-ray experiment with really good energy resolution. Clearing up this puzzle will be an important thing for them to do. So let's come back to charged particles. And so I'm sort of going from puzzles where I think we know the answer towards puzzles where I think we do not know the answer. So coming back to cosmic rays, I said that we could look for other charged particles as well as positrons and electrons. In particular, we can look for protons and antiprotons. So in the AMSO2 experiment, again, they measure the antiprotons, and it's not nearly as striking as the positron excess, but there is a little apparent bump in the antiproton flux at energies of about 10 to 20 GeV. And if you want to explain it with dark matter, you could do so by annihilating dark matter with a thermorelic cross-section at a mass between about 40 and 130 GeV. So this is nice. By a thermal cross-section, I mean the annihilation cross-section you need is right what you need to get the right dark matter abundance. So you could kill two birds with one stone that way. That's it. The problem here is the significance level of this excess is extremely highly debated. Depending on how you do your analysis, you can get a significance of 0.5 sigma or a significance of 5 sigma. So that's a place where just a better understanding of the instrument as well, and of the backgrounds is needed to be able to figure out if this excess is something interesting or just a fluctuation. So, and here's one excess, which I'm not going to, this is very new. It was just pointed out last year. This is based on looking at the 2 of the magnificent 7 neutron stars, which are isolated neutron stars close to us. And the claim is that if you look at the spectrum of these neutron stars, it has a high energy tail, which is not what you would expect from models of how they generally work. So one possible explanation, and this is kind of an exotic explanation, is that in the interior of the neutron stars, there are highly energetic interactions. And if there's such a thing as an axion in the spectrum of the standard model, those energetic interactions could produce axions. Then those axions, being weakly interacting, could fly out through the outside of the neutron star and convert back into photons in the magnetic field surrounding the neutron star through this oscillation process that I discussed before. And it turns out that if you say, okay, well, what kind of parameters will we need to explain the signal in that case? You find a region of parameter space for the axions that is like just below what is currently excluded by other observations. This is very new. It's worth keeping an eye on. There have been some new observations coming out that may challenge this region. I was talking to the authors, a little while back, and they told me that they're doing some more work on the signal models. So, maybe something to keep an eye on. But this is very much, I don't think we know what's going on. Okay, so in my last 15 minutes, I want to talk a bit about like one excess that I've spent quite a lot of time thinking about, which has also been around for about 10 years. But unlike the familiar positron, and unlike the AMSO2 positron excess, my confidence level that we know exactly what is going on here is significantly lower. So this is the Galactic Center Excess. So the Galactic Center Excess was an apparent new gamma ray component found in public data from the Fermi Gamma Ray Space Telescope back in 2009 by Lisa Goodenough and Dan Hooper. So basically the idea here is we look at the galactic center, we subtract off a model for the photons associated with the disk of our galaxy, so with the gas in the starlight and the disk of our galaxy. And what's left in gamma ray photons around a few GeV is a roughly spherical excess. So what's being shown in this top plot is before you do the background subtraction on the left and after you do the background subtraction on the right. Now, back in 2013, Dan Hooper, now this plot makes it look like the excess really only extends out about 1 degree from the galactic center. Back in 2013, Dan Hooper and I, in the course of a totally different analysis, found that it actually extended at least 10 degrees away from the galactic center. And the properties of the excess have been studied by many groups. It was confirmed by the actual experimental collaboration in this 2016 analysis. This lower plot shows the spectrum of the excess, that it's higher, that it peaks at around 1 or 2 GeV, and then it appears to fall off at both lower and higher energies. So if we're looking for a dark matter signal in the center of our galaxy, as I said earlier, we expect the dark matter to kind of pool and concentrate near the center. So a blob near the center is a good thing for a dark matter signal. We expect the background to look much more like the plane of the galaxy. We live in a spiral galaxy. When you look up at the Milky Way, that stripe of stars across the sky is the disk of the galaxy, and similarly in gamma rays. So this plot is like the galaxy spread out across in a rectangular grid, and the horizontal line along the middle is the plane of the Milky Way. So this is one way that we can try to discriminate in background versus signal. And we can also look at energy and spectral information. This bump-like structure is kind of what you might expect if dark matter was annihilating to some particles with some specific mass scale that subsequently decayed. So that all sounds promising. There were extensive studies on the Galactic Center Excess back in around 2014 to 2016. What they found is what I just told you. The peak is around a few GeV in energy. The excess is roughly symmetric around the galactic center and peak towards the galactic center. There's been later work, including by some excellent groups, including excellent Australian scientists like Roland Crocker, and Oscar Macias, who did his PhD in New Zealand, which said that actually it's not really spherically symmetric. It looks more like the bulge of the galaxy, maybe with a more symmetric component in the center. That would be very interesting if true, and I'll say more about this a bit later, but other works have found that a spherical signal is more preferred. So I think this is still a place where we maybe don't know the properties of the signal, but we think that it's pretty symmetric around the inner galaxy and that it has a peak at a few GeV in energy. And this plot here is just showing different regions around the galactic center. What does the spectrum associated with the excess look like? Okay, so it's a blob of gamma rays coming from the inner galaxy. Where could it be coming from? So the particle theorist's favorite hypothesis is that maybe this could be coming from dark matter annihilation. And it turns out that when you try to calculate again, okay, you do our exercise, what rate would you need if this is really dark matter annihilation? You find the cross-section you need is 2 × 10 to the minus 26 centimeters cubed per second. So this plot is data points for the excess without error bars, and the solid line is a fit from a dark matter model. And the cross-section is dead on what you would need to get the right relic abundance. So like, that's not a guarantee, but it's pretty nice. However, if you might also say, okay, so what are the best non-dark matter explanations? These other dashed lines on this plot are not fits. They are observed spectra of millisecond pulsars seen in gamma rays elsewhere in the sky. So these are spinning neutron stars that can emit over a wide range of frequencies, but including gamma rays. And I told you these error bars are statistical only, and the systematic errors are biggest at low energies. So this looks pretty similar, actually. So that has motivated a lot of discussion about, and I actually consider it currently the leading hypothesis, although not a slam dunk, that what we're looking at here is actually a population of pulsars in the inner galaxy. And then there are other astrophysical possibilities, like maybe there's some kind of outflow of high energy particles from the galactic center. Maybe that could produce high energy gamma rays like this way, like the signal that we see. And while this might be a little sad from a particle theorist perspective, from an astrophysicist point of view, like it's pretty cool. It would be a brand new pulsar population or some kind of new previously unknown outflow in the inner galaxy. So you can ask the question of how can we tell? So one way is to look for counterparts in other channels. We can look for pulsars in radio or X-ray. There haven't been detections here yet, but upcoming searches will pretty dramatically improve our radio sensitivity in particular. On the other hand, we could look for other possible signals of dark matter. You know, I was telling you on these automatic cross-checks. People have looked in dwarf galaxies, but because the galactic center is potentially such a bright source, it's actually not crazy that you could see a signal in the galactic center well before you see it anywhere else. The antiproton signal that I mentioned earlier, the one that could be 0.5 sigma or could be 5 sigma, depending on how you do the analysis, is actually in the right like cross-section and mass range to match up with this galactic center signal. But again, under some analyses, it's 0.5 sigma. So you maybe shouldn't, you know, drop everything to work on to follow that possibility. So there have been some hints of possible counterparts, but no confirmed detections. So we can look at the spatial shape of the signal on large scales. We'd expect the dark matter halo to be roughly spherical. It's just evolving under gravity. Observed stellar populations in the inner galaxy are not super spherical. So you can test these against each other. There's some arguments that the latter is a better description, which would suggest that we're looking at a population of stars, but it depends pretty strongly on how you measure the, on how you model the astrophysical foregrounds and backgrounds, so everything else that is producing gamma rays in the galaxy. So one possibility that I and others have followed up over the last few years, and which I'll give you the Cliff Notes version of in my 5 minutes remaining, is to try to look at the spatial shape of the signal on small scale. So if we're looking at a whole bunch of pulsars, then maybe there would be hotspots in the signal associated with the actual locations of those pulsars. Whereas if it's dark matter, we would expect it just to be pretty smooth. Now, of course, if none of the individual pulsars are bright enough to be visible as hotspots, they will just sort of blend into the background, then we won't be able to tell this way. But this could at least exclude the dark matter hypothesis. So this is the Pulsar Wars. And this was our new hope back in 2015 of telling the two apart. So the basic idea was that, again, you try to look at the granularity of the signal. That if you're looking at a bunch of individual pulsars, then the signal might look significantly more granular than if it was some smooth particle physics process that occurs anywhere where there is dark matter. So there were two main analyses in 2016, and I was on one, and both of us claimed evidence for finding this granularity, that there was a population of point sources in the excess. So our method was using the non-Poissonian statistics of fluctuations from an unknown source distribution, which I'll say more about a bit later. The second method, I'll just summarize a bit more briefly, which is to use a wavelet-based approach to try to pick out the peaks in this signal. So the wavelet method first. So again, in 2016, they said, we found a bunch of small scale power, must be point sources. So there was a recent analysis at the end of 2019 that repeated this wavelet analysis. And so now they said, okay, so we found a bunch of peaks, we found a bunch of hotspots. Now let's try to understand what those hotspots are. And they lined them up with the latest catalog of gamma ray point sources from this region and found that there was actually a ton of overlap. Like 115 of the hotspots found by the wavelet method were already in the gamma ray catalog. And the majority of those actually have been identified as either not in our galaxy or definitely not pulsars, which means that only a subsection of them are potential members of the Galactic Center Excess. Now you can say, okay, let's take those point sources, let's take those hotspots, let's look at the total emission in them, and it's about a factor of 5 below the total emission in the Galactic Center Excess. Furthermore, if you screen out these hotspots, so you just cut them out of your analysis and ask, okay, what's left? The Galactic Center Excess doesn't really budge. So the orange and blue lines here are showing the spectrum that you get to the excess before and after removing these point sources. So this tells us that there are definitely point sources in this region. Some of them might have something to do with the Galactic Center Excess, but the bulk of the emission really should be diffuse or originate from sources fainter than what we are currently detecting. That could still be okay for pulsars. Like I said, you can't really exclude the pulsar hypothesis this way, but it also doesn't exclude the possibility that the bulk of this could be coming from dark matter. Okay, so what about non-Poissonian template fitting? Now I have a limited amount of time, so I'll try to go through this quickly, but the basic idea is to use the fact that if you've got point sources in a region, even if you don't know where the point sources are, you can tell that there should be higher variance in the number of photons that you see in a given pixel. So imagine that I tell you that I've got this model, and my model predicts that I should see 10 photons per pixel in some region of the sky. And I ask you, what's my probability of seeing 0 photons or 12 photons or 100 photons? Now, the first thing you might do then is just use Poisson statistics. And if you do that, you'll find that there's a pretty decent chance of seeing 12 photons, it's about 10%. There's a much smaller chance of seeing 0 photons. And if you see 100 photons, there's something wrong with your model. Like you should not get 100 photons just as a statistical fluctuation on 10 photons unless you have a really large number of pixels. Our gamma ray resolution is not good enough to have 10 to the 63 pixels in the sky. But now suppose I tell you, actually, there was something I didn't tell you about my model. It's true that it predicts an average of 10 photons per pixel, but what I really mean is that I expect there to be a population of sources. I don't know where they are, but they're somewhere in this region. I get 100 photons per source, but only an average of 0.1 sources per pixel. So this gives the same expected mean number of photons, but now the distribution of how many photons I get per pixel is really, really different. Like now my probability of getting 0 photons is about 90%, because I just need to have a pixel where I just didn't happen to draw a source. My probability of seeing 100 photons is now much more respectable. It's now like 4 times 10 to the minus 3. So if I have 10,000 pixels, I might expect to see a few pixels like this. And my probability of seeing 12 photons is really tiny. So if I see 12 photons, I can say very strongly model 1 is favored over model 2. And if I see 100 photons in any pixel, I can say really strongly that model 2 is favored over model 1. So we can use this to try to disentangle the contributions from a population of point sources and a region with smooth emission, even if the overall spatial morphology of the sources and the smooth emission are identical. So that's what we did in 2016. We ran this analysis, we ran this likelihood-based analysis, and we compared the fit where we tested like just a model for the Galactic Center Excess that was purely smooth versus a model for the excess that could be some fraction of smooth emission and some fraction of point sources. So these plots are showing the posterior probability of getting a certain amount of flux attributed to the smooth piece versus the point source piece. This inset is the case where there's only the smooth piece, and the red in that case is the smooth component. And it came out to be about 7% of the total emission in this region, which was what we expected for the Galactic Center Excess. But then the larger plot shows what happens when you allow there to be a point source population in the region. And then you can see the red peak went to 0 flux. The orange peak is the flux associated with this point source population, and it came out as 7 or 8%. So what's happening? So this fit in 2016 told us that based on this likelihood analysis, the fit really wants to assign all the flux in the Galactic Center Excess to a population of point sources. So that's great news if you're looking for pulsars in the inner galaxy, but sad news if you are looking for a dark matter signal in the inner galaxy. And if I'd given this talk in 2016 or 2017, I would have told you, that's it. The Galactic Center Excess is probably really interesting astrophysics. We should find it in pulsar searches in the not too distant future, but it probably has nothing to do with dark matter. However, since 2016, there have been a few more developments, and now I think the situation is much more confused, although pulsars are definitely not excluded. And whenever I use this title, people point out to me that the Empire loses in the third movie. So, and that may still be the end of the story. So what happened in 2019 and 2020? So in 2016, as I said, the fit showed a pretty strong preference to assign all the flux in the galactic center excess to point sources, and that was about a 6 sigma preference. But together with Rebecca Lean, who was also Australian and did her PhD at Melbourne University, she came to MIT as a postdoc, and we wrote these papers where we showed that there's something a little fishy about this analysis. Because if you allow it to, so in our first analysis, we said it assigned 0 flux to the smooth component and 100% of the flux in the GC to point sources. But it turns out that if you let it assign a negative flux to the smooth component, it wants to assign a negative flux to the smooth component that is about 5 times larger than the excess itself. So it will give you a fit which is -5 smooth plus 6 point sources. And this is very obviously not physical. So there's something wrong. So what turns out to be wrong is that the background models that we're using to explain everything else in this region of the galaxy are just not sufficient to be able to do what we tried to do in 2016. And this was demonstrated in some nice papers by Chang et al. And Bushman et al. In 2019 and 2020, which showed that, yep, if you use the background models we used in 2020, things will go terribly wrong. You can use a more updated and sophisticated background model and show that, simulations with the more updated model show that if you try to model it with the background model from 2016, you run into exactly the kind of problems that we saw. So you can construct newer models which at least partially fix this problem, but unfortunately, we cannot at the moment build models for the Fermi data which agree with the data down to the level of noise, except by introducing thousands of additional parameters. So constructing newer models which fix this problem at least partially, you can look for the evidence for point sources, and it appears to still be there, but it's there at a much lower level. Like this becomes a 3 sigma detection instead of a 6 sigma detection. And Rebecca Lean and I were simultaneously working on this, and we found that there were some other problems. Like it wasn't just necessarily the background model that was causing the issues here. So what we looked at was the possibility that, okay, we're basing all this on a very rigid signal template for what the galactic center excess should look like. And that might not be the right thing to do, since we don't actually know what this excess is. And the question we're trying to answer is just like, is it smooth or is it made of point sources? So really, we're just trying to look at the variance. In the analysis that I just told you about, really, we're just looking at the level of pixel-to-pixel variance. But it turns out that the level of pixel-to-pixel variance can also be a proxy for your model is just bad. So let me give you just a really toy example. I say I have a model. It predicts equal flux in 2 regions. My model can be smooth or my model can be point sources, but it's going to predict that in these 2 regions, I have the same average flux. So let's say, call these regions 1 and 2. Then I look at the data, and the data says, okay, well, I don't have the same flux in the 2 regions. I have 2,000 photons in region 1, and I have 1,000 photons in region 2. So then we say, okay, well, but I didn't test that possibility. I only tested the possibility of my model that made from smooth emission or my model made from point sources. Well, so the best that I can do with a smooth model is say, I guess I got a 13 sigma upward fluctuation in one of these regions and a 13 sigma downward fluctuation in the other region. That's very unlikely. But with point sources, it's very easy to explain this. I just say I have 3 point sources and they make 1,000 photons each, and there are 2 of them in region 1 and 1 of them in region 2. So even though in this case I've said nothing about small scale power, I have said nothing about like pixel to pixel level variations, I've just said that if I have 2 regions where my model thinks they should be identical and they're not, that will drive a preference for point sources. So, I mean, this is not wrong. Like, it is true that it's much easier to explain this given the models that I've described if you have point sources, but it has nothing to do with the small scale granularity of the signal and everything to do with mismodeling it on a broader scale. So we can ask, does that happen in real data? So we looked at the real data, we looked at a 10-degree region around the galactic center, and we tried just offering the freedom to let the galactic center excess be different in the north and in the south. And when we added that 1 degree of freedom, we found that there actually was a pretty significant preference for a difference. In this particular case, with this background model, the north wanted to be brighter than the south by a factor of 2. And when we added this 1 degree of freedom, the preference for the preference for point sources, which should be, I think, order 8 or 9 sigma before we added this degree of freedom, dropped to less than 1 sigma. So really, in this case, the preference for point sources was being entirely driven by the fact that the excess was that our template for the excess was trying to describe something that wasn't really symmetric. You can do this in simulations as well. You can just simulate a case where you have an excess which is brighter in the north than it is in the south. You try to fit it with these pixel statistics-based methods as a linear combination of smooth emission and point source components. And what you find is that, so again, the signal is completely smooth. It's just brighter in the north than in the south. What you find then is that there's a very strong preference for point sources, which looks exactly what we see, like exactly what we see in the real data. And the inferred properties of those point sources are also really similar to what we saw in previous studies on the real data. This in a case where we know for sure there are no point sources associated with the Galactic Center Excess in this simulation. So this doesn't mean the excess is not made of point sources. This just means that the 2016 era evidence for arguing that the excess was made of point sources has some holes in it when you poke. Okay, there's been some other recent work on this. There was some nice work by Florian List and collaborators at, I think, from Sydney, looking at using a neural network to try to discriminate point sources from smooth emission in this region. They found that it preferred smooth emission, but their tests did show some bias in that direction, and sufficiently faint point sources would count as smooth. So this is very interesting, but maybe not conclusive. There was a nice analysis by Calore et al. And just very recently, using adaptive background models that have many degrees of freedom and can fit the data much better, and trying to do a photon count analysis like the one that I just discussed. They find evidence for both unresolved point sources and significant smooth emission in the region that we're looking at, but they don't try to figure out how the point sources are distributed. So they might just have to do with the galactic disk. There have also been some recent studies showing that, the pulsar interpretation probably can explain the galactic center excess without predicting too many bright sources, obviously, but maybe as we get better measurements of these, close to threshold points, pulsars or point sources, that might change. So how might we resolve this? Well, one way would be, as I mentioned earlier, to look at other frequencies. So this is a prediction from 2016 about being able to see the pulsars in radio. And if the galactic center excess really is made of pulsars, then upcoming radio telescopes could potentially see tens, or even once we get SKA, hundreds of pulsars from this population. Okay, sorry for going 5 minutes over, but I'm going to stop there. So the summary is basically, I hope I've convinced you that dark matter is a puzzle. It's more than 80% of the matter in the universe, and we don't know what it is. That is a problem for fundamental theoretical physics that we would like to solve. Astrophysical and cosmological datasets are enormously rich, and they can provide pretty stringent tests of the non-gravitational properties of dark matter, as well as gravitational effects over a wide range of possible scenarios. But very often the problem here is not the data, it's our ability to model the background and the signal. And I hope that this little tour of possible excesses in indirect searches has given you that picture. There are a number of excesses of varying degrees of significance that may be telling us about dark matter, but may also be telling us just about new aspects of conventional astrophysics. And in particular, the galactic center excess remains an open problem for the field, in my view. We may have found a new, hitherto undiscovered population of pulsars, but it's also possible that systematics in our analysis methods are fooling us into thinking that's the right answer. And there's maybe still a window for it to be a dark matter annihilation signal. Okay, thanks very much.
Thanks very much, Tracy. That was a really interesting and very valuable overview of the state of the field of research. I know that Tracy's happy to take some questions, and I see there are some coming up there. So I think the way to do that is to raise your hand. Is that the way it works? I think. Yes, I think that's right. Maybe I could be permitted to kick off the questions. You may have said this, and I missed it, or it may be implied in what you were saying. What's the current feeling about, you actually mentioned in your talk the galactic center excess. Well, what's the current feeling about the density distribution of matter in the cores of small galaxies? Is it still the case that that's predicted to be peaked more than observations suggest, or has there been some change in the thinking there?
I would say it's still a bit ambiguous. So right, so this is like this is the core cusp problem. This is the statement that If you take models with only dark matter and you ask what is the density distribution in clouds of dark matter, then you see that there tends to be a fairly steep peak, which goes like roughly like 1/r towards the center.
Yeah.
Once you can modify that by different models of dark matter, like if you have self-interacting dark matter or warm dark matter or dark matter that's extremely light, then it changes the shape of that. And sort of the standard dark matter is just a cold non-interacting particle picture. You expect this cusp. And observationally, I think it still is observationally true that at least in many dwarf galaxies, you see a profile that is flatter than that. Now, the problem is that as soon as you start adding like any baryonic matter into the centers of these galaxies, so like the stars formed at some point during the, so in the process of star formation and stars going supernova, they can transport material out of the dwarf galaxy, and that can drag along dark matter with it just gravitationally. And it turns out that because the potentials in these small galaxies are just not very deep and are pretty shallow, it doesn't take a lot of ordinary matter, like it doesn't take a lot of stellar activity in order to significantly perturb the dark matter distribution. And basically, if you slush the dark matter distribution around, then the effect is usually to flatten out the cusp. So as I understand it, and definitely if there are experts in the audience, they should speak up and tell me if I missed something in the last couple of years. But as I understand it, the status at the moment is that for the range of dwarf galaxies whose slopes we have currently measured, it's really hard to say that you can't do it with baryonic physics, because for the dwarf galaxies that we can currently see, they have quite a few stars associated with them, because otherwise we wouldn't be able to find them. But if you could go to even smaller, like dark matter clumps, dark matter dwarf galaxies, then you do expect to see a point where there's just not enough baryonic matter to induce the stellar feedback that perturbs the centers of the galaxies, and you would get into more like the dark matter only situation where you would expect to see the cusps. But the problem is that if there's no baryonic matter, then it's like, how are we going to find the things? So yeah, so but there are some proposals to try to push down that threshold with I think some hope of getting to faint enough objects that you would expect to see the cusps. But I think at the moment the status is mostly like the more work has been done on simulations of baryonic physics, the more it seems to point in the direction of, yeah, baryonic physics can do a lot to perturb the centers of the halos. So
I see there are a few questions queued up in the Q&A panel, and also Rosemary Mardling has her hand up. So I might, I'm just going to enable Rosemary. Are you happy to ask your question, or would you write the one that you posted?
You can, I'll have to read it out, or you can read it out.
All right.
Well, I'll say it. Okay, so yeah, I'm just saying, in the BBC News today, and elsewhere, there's an article, New Dark Matter Map Reveals Cosmic Mystery, and it talks about results from the Dark Energy Survey collaboration, which suggests that the distribution of dark matter is much smoother than expected. And I put a quote from the famous Carlos Frenk, who spent his life thinking about these things. I spent my life working on this theory, and my heart tells me I don't want to see it collapse. But my brain tells me that the measurements were correct, and we have to look at the possibility of new physics. Then my stomach cringes, because we have no solid grounds to explore, because we have no theory of physics to guide us. It makes me very nervous and fearful, because we are entering a completely unknown domain, and who knows what we're going to find. So I was going to ask you to comment, but I was going to also mention that my money is on the recent work of Andre Madère of Geneva, which is based on the idea that physics should be scale-free on large length scales, and it predicts just about every observation that we see: galaxy rotation curves, velocity dispersions, and galaxy clusters, etc., even inflation. And it's an old idea that physics should be, scale-free, and basically it removes the cosmological constant, and you get everything all on the one plate. But anyway, I just wondered if you could comment on this dark energy survey
Yeah, unfortunately, because this just came out today and I've been in meetings all day, I don't have a lot to, yeah, so I'm just, sorry, I'm just
No, that's okay. It's hot off the press, right? So
yeah, so it sounds, right, I mean, so it sounds like, yeah, okay, yeah,
that's
so
okay.
right,
That's
yes,
all right.
so I guess, you know, I mean, so for first pass, I mean, like, I mean, more data is always great. Like, I mean, I think, you know, Carlos's comment, I mean, like, I think it's true that, you know, we don't have like one clear, well, I mean, maybe in your case you do, but I mean, the field as a whole doesn't sort of have one clear picture for what dark matter should be, or how dark, or, you know, how dark energy would behave once you go beyond the standard cosmological model. So, I mean, as I explained, there are, you know, there's an enormous number of possible ideas for what dark matter could be. And I think there is a potential worry that it's just like, you saw a new observation. Well, you know, 1,000 theorists will all try to fit their favorite model to the data. And maybe like, you know, 100 of them will be like, look, I have a model that explains this data point. And
yeah,
and
well,
then it's sort of like, okay, is that a useful way to make progress?
There's huge industries, right, and particle physics and cosmology, but you know, really, there's a simple solution, and that is to remove the cosmological constant, and as Einstein originally wanted to do, and people were thinking deeply about this back then, and still are. We don't need any more particles or strange energy or anything. It's all in the physics and symmetry principles. This is not a Mond theory. It's a first principles theory.
I'd definitely be interested. Yeah, I mean, if you shoot me some references, I'd definitely be interested to look more into it. I mean, we do have. I mean, I guess that the issue with a lot of modified cosmologies is that between the combination of like the matter power spectrum and the observations of baryon acoustic oscillations, and then observations of the cosmic microwave background, we have some pretty precise rulers of how the universe behaves at different scales, and
this, any theory has to be consistent, and this is looking good at every turn. So keep an eye out. But yes, I'll send you.
I will. No, thank you. Yeah, it's. I mean, it looks like they're basically saying that there's a mild. I mean, it llooks like the DES stuff at the moment is sort of like a mild difference in the clumpiness of dark matter on different scales, which, yeah, I need to read the article and find out what scale they're actually talking about it, because there's been a lot of like discussion about, you know, how clumpy should dark matter be on relatively small scales, and that's almost completely unknown, because again, going to David's question, it depends pretty heavily. Well, it depends heavily on two things. It depends heavily on the effects of the ordinary matter on the dark matter, but it also at that point starts to depend in detail on like, when did the dark matter, assuming that, you know, dark matter exists, when did the dark matter stop interacting with the visible matter in the early universe, which is something that is pretty model dependent, and we don't have a good handle on. So yeah, so like, I mean, depending on the scale, it might be like, yeah, this is just like a messy region that our predictions are not great for. But at higher scales, there are certainly like unresolved mysteries in cosmology beyond the ones that I've told you about. Like the Hubble tension is a famous one, that when you try to measure the Hubble parameter of the standard model in the present day or at the CMB, you get slightly but statistically significantly different answers. So if there are more hints to ways in which we might perturb away from the standard cosmological model, that would be very interesting. Anyway, I'll take a look at the article for you. Sorry, I don't have a good reaction to it right at the moment.
Thanks very much for that question, Rosemary. We've got a question from Christopher Graham as well. Christopher, would you want to ask your question, or would you prefer if I read it out? Have I enabled you?
Well, the core of my question, sorry about Leonardo da Vinci there, the core of my question is mainly about gravitational waves and the beginnings of using that as an observation technique. And I'm just wondering if you may be able to find clues for dark matter using that into the near, let's hope, near future. Because to date, the only sure interaction you seem to have with baryonic matter is via gravity.
That's right.
I also make the point that maybe in the future, once it's all done and dusted, and dark matter is just part of a new standard model, they'll look back and say, oh, well, the first detection was actually the way galaxies rotate, because that's how we often work. We get a bit retrospective and say, oh, that was the first detection. So that's my question.
I mean, like even in the 1920s and 1930s, people were noticing that clusters appeared to be noticeably more massive when you tried to look at their gravity than when you looked at than when you just did a census of all the visible stuff within them. So I mean, it could even go back that far. But yeah, so I mean, to get at your question, yeah, gravitational wave astronomy for dark matter physics is super interesting. The status at the moment is because there's a fairly limited set of kinds of gravitational wave observations we can do, so we can that we can plausibly see. So we can look for gravitational waves from very violent events like black hole or neutron star mergers, or we can look, or in the future we may be able to look for gravitational waves that were produced very early in the universe's history when the universe was much more energetic, and those waves have propagated forward to the present day. In both of those cases, there are possible classes of dark matter models that could be probed by gravitational wave signatures, but they sometimes require something a little bit non-generic to happen. Just for example, there's a class of, if you have very light, ultralight bosonic dark matter, then you can have a situation where, I'm just trying to think about the best way to describe this. So you can get a configuration where the wave function of the dark matter in this case is macroscopic. If the wavelength of the dark matter is comparable to the event horizon of the black hole, you can get a situation where the dark matter dark matter black hole system behaves like an atom, with the black hole as the nucleus and the dark matter and the excitations of the axion field or whatever, basically acting like the electrons in orbit around the nucleus of the black hole, because of this resonance between the wavelength of the axion and the event horizon and the Schwarzschild radius of the black hole. Now, when that happens, you can so in that case, the black holes in the universe can be sort of these extended objects that have this dark matter bound states surrounding them. And in that case, whenever black holes collide with each other, you potentially excite the bound states of the system, and that can give rise to a modified gravitational wave signal. So that's a case where gravitational waves could potentially provide a direct probe of dark matter models, and it actually places, I think, the leading constraints on dark matter within a particular mass range, but only in that particular mass range, because you need this connection between the wavelength of the dark matter and the Schwarzschild radius of the black hole. So that's an example of a kind of analysis that you can presently do with gravitational waves, but yeah, but it's somewhat narrow. So I mean, there's, if we could detect arbitrarily faint gravitational waves, we could do so much with it. But at the moment, because we need these really high energy, we basically at the moment we need we need very dense objects to be involved to see anything. It means that somewhat limits what you can do for these searches. But it's a super interesting field of research. And I mean, if we can see gravitational waves from the very early universe, that could allow us to probe back to times that we just cannot see with photons because the universe is opaque once you go back far enough. And that, that has the possibility to tell us about, early matter-dominated epochs in the universe's history or early phase transitions, and really give us a view of what's happening for high-energy physics. And I guess you also had a comment in your question in the chat, I'm just looking at it, about why do we assuming that the dark matter produces equal amounts of positrons and electrons. Yeah, it's not definite. It doesn't. You can come up with models, and I've seen a few where positrons and electrons are produced in unequal amounts from dark matter annihilation or decay. So that said, that is, that's a useful approximation, but it doesn't really change how you search. If you assume that dark matter was going to 90% positrons and 10% electrons, it would change what class of models explains the AMSO2 positron excess. But it wouldn't really dramatically change the kind of search that you do to look for an excess in positrons. It would just change the interpretation. But you're right. For all we know, dark matter could carry standard model quantum numbers. It could have, it could have its own weird symmetries. It doesn't need to behave in any specific way beyond the things that we know, that it doesn't have particularly strong interactions with the standard modeler itself, and that it gravitates.
Well, that's probably a pretty good segue into Michael Hall's question. I'm not seeing Michael on the list at the moment. I apologize, Michael, if you're there and I can't see you. I might just read your question.
He might have had to leave, but I mean,
Yeah,
if so, I guess it's recorded so you can see.
He had a couple of interesting questions. The first was, why don't we expect dark matter to clump into point-like sources distributed through the galaxy because of lensing observations? Primordial black holes are primordial black holes ruled out as a cause of the galactic excess?
It's a really good question. So dark matter could be, right, so but primordial black holes could be dark matter, but only primordial black holes in a relatively narrow mass range. The range that is usually thought to be open is from about 10 to the 17 to 10 to the 23 grams, which corresponds to roughly the range of masses of objects in the asteroid belt. So these are not black holes that would be produced by stars collapsing or anything. These are black holes that would have been produced very early in the universe during inflation, and which have then just, gone through the universe, mostly not interacting until the present day.
Is the lower limit on that set by the fact that smaller black holes would have evaporated? Is that what?
Yeah. So it's not actually that they would have fully evaporated, but that they would be decaying rapidly enough to make a signal that we can see. Like they would have been emitting X-rays and gamma rays at a level that we would have found in the searches that I've just been talking about. That corresponds to a lifetime about like 8 or 9 orders of magnitude longer than the age of the universe. So if you go down another few orders of magnitude, they would actually be short-lived. But in this range, they're long-lived. But we would see them because they would be glowing. So. But yeah, that's right. So that's what that lower bound is set from. The best limits are actually from X-ray observations of our galaxy. Actually, the best limits that I know about are set by a really, so my collaborators and I did this really simplified analysis of some very old X-ray data from a couple of decades ago, and to our shock and somewhat horror, that turned out to give the best limit at the time on decayed black holes. I mean, shock and horror just because it was a really cursory analysis and the data is kind of old. So that's a place where we might actually be able to do quite a bit better with time. There have been some more recent papers about how future experiments in sort of hard X-ray to soft gamma ray range could potentially improve that limit. So yeah, so I've said dark matter can be primordial black holes. So why was I earlier saying, oh, the Galactic Center Excess, if it looks like point sources, it's probably not dark matter. The issue is that if the dark matter was asteroid-sized primordial black holes, you can ask how many of those black holes there would be in the inner galaxy. And the answer is a lot. So, I mean, like the answer is a very large number. So what you would then expect is that, like, even if those black holes were radiating in gamma rays, you would expect to be in the limit where you're seeing either 0 or 1 photon from every black hole. So like that, even though they're point sources, that's smooth emission. Like that's the definition of smooth emission, that you don't see 2 photons from one point-like source. So it has exactly the statistics. This is kind of what I said when I said those like smooth versus point source tests that I was talking about earlier. They can't actually exclude the possibility that it's point sources. They can only exclude the possibility that it's point sources brighter than a certain level. But I mean, if in the cases where you want to explain the whole galactic center excess with point sources that we can actually see at the moment, you're probably, I think, talking about like something in the neighborhood of tens of thousands of sources to make the whole excess. If you take the total amount of dark matter in the inner galaxy and you divide by the mass of an asteroid, the number you get is a lot bigger than tens of thousands. So yeah, so it's just like, I mean, so like from that perspective, from just like, are they point sources or not, there's nothing wrong with having like lots of little tiny dark matter black holes, but it wouldn't look like point-like emission under the definition of point-like emission that these like wavelet studies or statistic studies are using. Right.
And then the other part of Michael's question was, why don't we expect dark matter to dump into point-like sources?
So yeah, I mean, so the basic reason, in cold dark matter models, the reason why the dark matter doesn't really clump is basically because it can't radiate. So it doesn't have the ability to shed energy and angular momentum by radiating a massless particle like a photon, because it doesn't talk to photons. So it is possible for dark. So it's analogous to like the planets going around the sun. Like the planets are going around the sun, but they don't fall into the sun because they have angular momentum, and they don't have a good way to shed that angular momentum. Okay. And they're not colliding with anything very often. So dark matter is like that. Like it's in an orbit, you know, it'll have some angular momentum. It's very hard for it to shed that angular momentum. So it just basically keeps going around. There is a gravitational instability that over time causes the orbits to decay. But you can work out what the time scale is if the interactions are purely gravitational, and it's much longer than the age of the universe, like many orders of magnitude longer than the age of the universe. So now, if you let the dark matter have some non-gravitational interaction, if you let it radiate, if you let it couple to like some new very light particle, so it's like a photon and it can radiate like ordinary matter radiates photons, then it will clump like crazy. Like, so this is called dissipative dark matter sometimes. And if you want to get dark matter clumps, this is the way to do it. If you don't allow it to radiate, but just allow it to interact more often, then basically that speeds up the time scale on the gravitational instability. And this leads to what's called core collapse. So where in these strongly interacting models, you start out in the centers of galaxies, you start out by sort of flattening the dark matter distribution, but over time you can actually get a very intense cusp through this core collapse mechanism, which is just gravitational instability, gravithermal instability. So short answer is dark matter could collapse into compact objects. For our standard sort of weakly interacting main thing affecting its motion is gravity dark matter. The time scale for it to do it is longer than the age of the universe.
Well, that's really interesting. I don't see any other questions queued up. There was another question from Michael, but that could probably be handled offline. If I could probably be, sorry?
Oh yeah, I mean the other about like dark matter signals from
that's
like
right,
gravitational wave and optical detection. Yeah, I mean I guess we sort of talked about those already when I was like, well, you know, maybe like dark matter atoms around black holes could modify black hole neutron star collisions, but you need to be in a fairly special mass range for that to happen.
Well, if I could be permitted the final question, could you perhaps say a few comments about what's the current view about the modeling the the Tully-Fisher relation, the baryonic Tully-Fisher relation that comes very naturally out of modified Newtonian dynamics type of arguments, the fourth power relationship for the velocity for stars distant from the galactic center. So what's the current thinking there in relation to dark matter models? Can that make a prediction?
So my understanding, and again, this is not my like greatest error. This is I work on dark matter, but understanding modeling the structure formation of dark matter over time and how it interacts with the baryons is like a specialized job that involves building giant simulations, and that's not my particular area of expertise. That's it. So my understanding, based on like the last couple of years, is that So the business here is you build giant embodied simulations and then you put in a prescription for the ordinary baryonic matter. And this involves like modeling what's called subgrid physics on some scale, because you cannot resolve within your cosmological simulation everything that's happening to the ordinary matter. So instead, like you put in some prescriptions for, okay, supernovae are going to dump this much energy with this kind of time dependence, or there's going to be like ionizing radiation coming out with this time dependence in this spectrum. So you put in various knobs to try to model the subgrid physics, and then you turn the knobs and try to match the data. So like as I understand it, that is basically the exercise. So my understanding is that when you run these simulations and you match, and when you run these simulations and you turn the knobs and you try to figure out how to explain what we see in the present day universe, then you can get something that looks, that replicates the universe like very well, including the Tully-Fisher relation. But I don't think, as far as I know, like I don't think there is a sort of like simple, intuitive, say it in like 2 lines explanation for why you would expect to get the baryonic Tully-Fisher relation in this case, as opposed to, well, when I fit the data, when I fit my model to the data and then I run my model, then I predict something that looks like the baryonic Tully-Fisher relation. So I guess MON generally, I'm very glad that people are still thinking about it. I think people should think about alternatives to conventional wisdom in fields. I think that's a good thing to do. The reason that I would personally bet in the direction of dark matter or something like dark matter being the answer is probably twofold. One is that in general, when I compare MON-like theories to dark matter-like theories, it has usually been true that the MON-like theories have trouble getting the cosmology right and the large-scale behavior right. And that is where the physics is relatively simple and we think we understand what's going on. Whereas the dark matter scenarios, usually the problems with it show up on small scales where the baryonic physics is critically important. And it's just much easier for me to believe that the apparent discrepancies are coming from the baryonic physics is critically important and really complicated, and we're dealing with it at the level of simplified subgrid models, then that, you know, then I mean, it's easier for me to believe that than to believe that we're just going to like find some easy fix to something that gets the cosmology wrong, given that the physics of the cosmology is basically the physics of a four-stamped harmonic oscillator. Like it's, so you know, like there's that. And then my other reason is, I guess, just like, to me, dark matter is the simpler explanation by miles. I mean, you know, on one hand, I mean, in some ways, MOND would be the much more interesting result. Like, I mean, I like dark matter. I think, as I told you, the dark matter could potentially be a key to unlock lots of other physics. But I mean, it's also possible that we could solve the dark matter problem. And basically what we figure out is like, there's one new particle. It's like a heavy neutrino. It's a lot like neutrinos, except it's heavier and kind of slow moving. And like, that would be really interesting, but it would be, you know, we found one more particle. And I mean, like that would still be really exciting. You know, I would like to know about it, but it wouldn't, I mean, it wouldn't necessarily elucidate some new fundamental physical principle. It could just be that there's some like nearly inert stable particle in the universe. Whereas like MOND would be a new physical principle. I mean, modifications to our theory of how gravity works could potentially teach us something new. So I mean, you know, sometimes people are like, oh, you know, you just want your exciting theory, and I'm like, no, like dark matter to me is the Occam's razor option. It's there's one new particle and it's really boring and it just behaves like ordinary matter, except that it doesn't interact as well. So yeah, that's but yeah, so like, I mean, for that, I would actually love the answer to be that, you know, there was something really, you know, cool and unexpected going on in our theories of gravity. That sounds really interesting. Or I would love it to be dark matter to be telling us something really, you know, interesting and new about like some new dark sector or some new fundamental forces of nature. But I mean, of course, I would settle for it if it turns out dark matter is a heavy sterile neutrino. Like that would be interesting. It is what it is. I mean, the universe does what it does, and you know, all we can do is try to figure out what it's doing.
Well, thanks very much, Tracy. On behalf of everybody, one thing that's missing in this digital technology is a way to get a round of applause. So on behalf of everybody, I'll give a round of applause to Tracy.
Thanks a lot, Tracy.
Thanks.
Thank you very much.
Thanks very much for the invitation. I'm very, very, very glad I got to tell you about this.
Thank you.
Yeah. Oh, very good. Thanks.
Keep an eye out on various excesses, even if they are probably pulsars.
Thanks, Tracy, and thank you everybody who attended the webinar.
Thanks very much, everyone, and thanks David and Murray for organizing.